All right, welcome to another IAEI News Live. My name is Thomas Dimitrovic. Hey, everybody. I just want you to know this is a recorded session. Forgot to say it. Shh. And today is 4th of July, July 4th. So I thought, what better topic than a discussion about arc flash for a July 4th discussion on IAEI News Live. And it all starts now. All right, well, welcome back. Okay, so we're going to talk arc flash. We're going to talk incident energy, and hopefully you'll have your copy of the 2023 code book, and also we shouldn't forget about I think I have get your copy of 70E. Now, I have a 2021 edition, but you know what is the latest edition is the 2024, and it is out. So we should be looking at the 2024 edition of 70E, which I have to order my hard copy. I have it electronically, but regardless, maybe I will call it up over here. So let's talk arc flash incident energy. So when we think about incident energy, you think about a rapid release, an unintended rapid disassembly of a piece of equipment in the field, right? So an arc flash event, you're letting the smoke out. You don't want to let the smoke out. Just saying. So some statistics. OSHA estimates that on average, there's at least 8 burn injuries from arcs that occur every year, involving employees doing work covered by OSHA rules. Now, remember, OSHA is a lot more than just electrical. So when they say employees doing work covered by OSHA rules, that could be anybody. And this is in Informative Annex K. And I'm just going to call up my NFPA link on a different computer. And I know you will be calling up your copy of NFPA link. So 70E is available as a 2024 let me go to view all publication, type in 70 Edward, enter. There it is, the 2024 edition. Man. So Informative Annexes, and Informative Annex K is still there, and a very good resource for you because there's a lot of information in Informative Annex K, and K.3 has not been modified during this last change for 70E. Now an arc flash. Okay, so I believe, let's take a look at definitions. Arc flash is still not a defined term in 70E. Now, when you have a lack of a definition, you know what that means? We have the opportunity to make one up. So I came up with this. An arc flash is the light, heat, sound, and gases produced as a result of a rapid release of energy, an unintended rapid disassembly in the field, due to an arcing fault sustained by the establishment of a highly conductive plasma. So here's what happens when you have an arc flash event. You initiate. If you think about just if you've ever experienced a sparks and whatnot, because say you're working on the vehicle and you caused a spark because of the battery. You're connecting the battery, disconnecting the battery, whatever. That's a very, very, very small arc flash event, right? It's still, there's energy there. You're releasing energy. It's just not significant enough. When you get to these higher voltages and you get to the higher fault currents in the applications that we work around, you can create that initial spark that may melt some of the plastics or whatever is around it. But in essence, what happens is you create a little cloud of plasma, basically. And it's a conductive environment. If you could contain it, if you could put it into a cup and then analyze it, you would find that there are a lot of different types of materials and gases that are being released when they have an event like this, and that those gases are conductive. Now they have an impedance, right? But it's basically a cloud in air that gives a path for current to flow. So, NFPA 70E, they define an arc flash hazard. I think you probably have to go to hazard, electrical hazard, and the electric shock hazard, an arc flash hazard. Now, an arc flash hazard is a source of possible injury or damage to health associated with the release of energy caused by an electric arc. So there's an informational note that references 110.2b, exception number 1, for information regarding normal operation. And speaking to, I don't know why they would have, so they have an informational note reference to 110.2b. 110.2b 110.2b has an exception 1, which is normal operation of electric equipment shall be permitted where a normal arcing condition exists. A normal operating condition exists when all the following are satisfied. The equipment is properly installed, the equipment is properly maintained, the equipment is rated for the available fault current, the equipment doors are closed, all equipment covers. So that is informational note. I mean, that's exception number 1. So it says, see 110.2b, exception number 1, for further information regarding normal operation. The likelihood of occurrence of an arc flash incident increases when energized electrical conductors or circuit parts are exposed. So what they're trying to do is say, look, here's the definition of an arc flash hazard. And by the way, the likelihood that an arc flash will occur is higher when you have exposed energized parts, etc. When you're not following, when you're not meeting that exception of 110.2b, exception number 1. So I guess I can see the relation. But in any case, the arc flash hazard is something we have to think about when we're doing justified energized work, which is another aspect of 70E that we have to just keep in mind, that we're supposed to establish, your goal should be to establish an electrically safe work condition so you avoid any possibility of an arc flash hazard. Now, I typically, whenever I talk about these things, I share this article. I was sent this a long time ago, an email by an industry friend of mine, another fellow educator, and he said he sends me this email, and I read it: worker burned in a Walmart accident, that he passed away, and I responded, boy, my heart goes out to the family. Thanks for sharing. And then he gave me a call as soon as I sent the email, and he says, "You didn't even read it." I said, "Yeah, I did. You know, a worker was. I get it. I mean, I read it." And he goes, "No, you did not read it." And then he walked me through an observation. The first observation was that the report was October 16th, 2006. And the event occurred in that same year in August. 51 days of an individual severely burned in intensive care in a burn center for 51 days until he passed away. That's a lot of suffering right there. And I was like, wow, I never did that correlation. Seemed like a simple article, but the accident occurred on the 26th and he passed away on August 26th, and he passed away October 16th. And then he says, that's not it. That's not all. He says, keep reading. If you look down at the bottom, it says the other two workers, 29 and a 27-year-old, they're also in Wishard's burn center since the accident. They are still in the burn center. And they're listed in serious condition. So an arc flash event and a burn injury is not something that you just get something. It's not like you go get a cast and you go home. It's not like you have an operation and you go home. This is something that there's a process, and there's a lot of scars that are left afterwards, both physical and emotional. So what is an arc flash? Arcing faults. So what we try to do is we try to understand. Here's the thing. We need to understand what these arc flash events are, how they're caused, understand how do we calculate the heat, and then we need to wear proper personal protective equipment. So what I'm going to do in the next few slides or so here, I'm going to help you understand how do we know what calories per centimeter squared, how much heat is going to be emitted. What can we calculate? What can we not calculate? What are we trying to calculate, right? Why are some applications have a higher incident energy than other applications? So that's sort of my what I'm going to try to convey in the next however many minutes. All right. So what we do know is that there are two types of fault currents. What we typically calculate when we're evaluating equipment, we will calculate the bolted fault, high short circuit, maximum amount of fault current that you can have delivered at a point in the system. That's your bolted fault current. The next data point, when you think about what happens in many instances, what causes the fault. In some cases, you might have, what's shown here, a wrench that falls into a piece of equipment, a tool that falls into a piece of equipment. Maybe it's a rodent that gets into a piece of equipment. Water, anything that would initiate a fault, but it's not a bolted fault. When we say a bolted fault, we're talking a fault of zero impedance. As if there's the thickest copper bar that has the lowest, almost zero impedance, establishing a fault from phase to phase to phase. So this right in here is zero impedance, Z. This, this type of fault, an arcing fault, is one that has an impedance value. And we show a wrench. But remember in the beginning when we talked about that plasma cloud, the current flowing through air, that has an impedance as well. I may initiate, if I drop a wrench on 3 phases, do you think that wrench is going to stay there? It's probably going to get blown away. Or it's going to be evaporated because of the heat. And then that cloud that envelops all around those phases is going to have currents flowing through the air, phase to phase to phase, and it's going to create a lot of additional plasma and additional shrapnel and other particles to be expelled from the equipment. That copper bus is going to be vaporized, and all of that adds an impedance and gives current a path to flow basically through the air. And that will produce a lower fault current value than the 3-phase bolted fault. It will be a lower arcing current. Remember that arcing current, if I would draw the diagram, I would have an impedance in series with the current that would bring the current down. If the same voltage, I bring the current down, and I have lower currents, which would be a percentage of the bolted fault current. So we know how to calculate bolted fault current values. We do it on a daily basis. We'll calculate that to evaluate interrupting ratings and short circuit current ratings. But then the question becomes, how do I calculate an arcing fault current? There's equations for it, and we're going to get to it. So we have to design for the worst case conditions, right? But in some cases, the bolted fault current for interrupting ratings and short circuit current ratings, that is what I will do my equipment evaluations. That's the worst case for an overcurrent device trying to open and clear the fault, and the worst case for a piece of equipment and all of those magnetic forces letting that current pass through it. The arcing fault, though, is a lower value. The lower values of arcing current can produce higher levels of incident energy, and I'll help you understand why that's the case. But the worst case condition for interrupting ratings and short circuit current ratings may not be the worst case condition for an arc flash calculation. Keep that in the back of your mind, because as we move forward, hopefully you're going to start to understand that. So the amount of energy that is released during an arcing fault or during an arc flash event is dependent upon how much time we let the current flow. Remember, incident energy, for the most part, and you'll understand why I'm saying for the most part, it's a little bit later. It's about current and time, how much current is flowing, and really how much time that I am permitting the current to flow. So duration is critical. And it's critical to understand this concept, because I have to understand what I can control and what I cannot control. I may be able to control how much time I let current flow. I might not have too much control over how much current flows. Unless I'm in the design phase, right? If I'm in the design phase and I want to make sure that I have very high fault current, I can increase my conductor sizes. I can shorten my conductor runs, less impedance. right? If I want to make sure that the current fault currents are very low, I can make longer conductor runs. I can add a 1-to-1 transformer, which adds a lot of impedance. There are a lot of things that I can do, but that's in the design phase. After the fact, it is what it is. The amount of fault current flowing is the fault current. That's all I can. The only thing I can control is how much time I permit that arcing fault current to flow. So remember the parameters. First, I need to know bolted fault current. We have equations for that. I need to know the arcing current. We need equations for that. Hint, hint, hint. And we need to know arc flash. So in 2002, IEEE 1584 was first released. That was 2002. Think about other things that were going on in the National Electrical Code. In 2002, that was when we introduced Section 110.16 for arc flash labeling in the NEC. That's the same year that 110.16 was introduced, and we ended up with a, hey, this could be a hazard type of label. Today, 110.16b closely reflects the work of IEEE 1584 committees and the testing that was done. The latest edition of this document is 1584-2018. So in 2008, it was introduced in 2002. We did a lot of testing and research, and an update is provided 16 years later. And there's a lot of information that is now available in this document, but I'm going to help you understand the significance of IEEE 1584. So if I'm going to do an arc flash analysis, if I want to determine how much energy is at any point in the system, I need to do these 5 steps at each piece of equipment within the power distribution system. First, I need to calculate the 3-phase bolted fault current. We have many industry resources for doing this. I'll tell you the ones that I've used. They're up there. That's my red book and my buff book. I have IEEE, the IEEE red book and the IEEE buff book are 2 resources that I've used in my after I graduated with my electrical engineering degree, and I actually got into doing systems analysis studies. In fact, my senior year is when we got into doing calculations, but I obtained these resources right about when I graduated from college. But great resource to help us understand how to calculate the 3-phase voltage fault current. Second, we need to calculate maximum and minimum arcing currents. Now, in reality, I may calculate the maximum and minimum bolted fault current values as well. I'm going to put that in here. 3-phase bolted fault current values, right? And we're going to say max and min. So, and the reason that's important is because I need to calculate maximum and minimum arcing fault values, because the maximum or minimum could yield the highest incident energy. So once I know my currents at every point in the system, I know my maximum and minimum short circuit values. And when you say, well, how do you calculate a minimum short circuit value? Here's one thought process here. Let's go back to this. I'll give you an example. If I had, let's say that I have a panel board like this, right? So I would have I short circuit coming from the upstream breaker. If these are motors, I'll also have motor contribution if those motors are running and if they're not on a variable frequency drive, blah, 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 blah. So what I would want to do is for Imax, all motors on. For I minimum, all motors off. That's one of the most simplest examples of a maximum and a minimum fault current value. So the bolted fault current value. Now, you'll help, again, you'll understand why this is important as we move through this discussion. So we're going to calculate a maximum and a minimum arcing current value. You know what I need? Actually, I need a white. I guess I don't get white, do I? Oh well. All right. So I need a maximum and a minimum arcing current value for each of these. Now the third thing, now we're going to calculate, well, for the second thing, we have to calculate arcing fault current. And this is what I use IEEE 1584 to do. IEEE 1584 tells us that an arcing fault current is a fault current flowing through an electrical arc plasma. Remember we talked about that plasma cloud. That's through air. It's through this charged ionized cloud of energy that gives the current a path, but there is a resistance. So there's your plasma cloud, right? That plasma, that bright event, we initiate an arc flash event, and that light, that gaseous cloud is your plasma. That's your vaporization of your aluminum, your steel, any other plastics that might be in there. That ionized cloud, again, creates a path for current to flow, and it has an impedance. And it introduces an impedance. Now, the challenge that we have is, how do I calculate? Remember, I know how to calculate a three-phase bolted fault current value. The impedance is 0, but what is the impedance of that plasma cloud? That's the challenge. That's what IEEE 1584 does for us. It gives us those equations. Now, I'll tell you what, how we came up with that. So when for IEEE 1584, what we did is we took that arcs in a box. I'm trying to see if there's a good picture of it. No, I don't have a good picture of it. So we take an enclosure with electrodes. We initiate an arc flash event. And so what we do is we take a box. Take a box. Gosh. And we put 1, 2, 3 electrodes. Boy, we're testing my drawing capabilities. Imagine he's looking at you. Then we take a wire and we connect each of these together. It's a very small initiation. We know it's going to basically act like a fuse in air, and it'll initiate the arcing fault, create that plasma. cloud that we're talking about. So, and then what we do is on the front, we put these sensors. I don't know how to draw a sensor. We'll just draw it like that. And we measure the heat that's generated at so many inches away, say 18 inches away from the event. And then what we do is we create a curve. And we say we're going to do this across the bottom is bolted fault current value, bolted I short circuit, and we'll call this arcing. I arcing. I arc. All right. So then we say, okay, let's hit it with 10K. And then boom, we record a number. And we do it again. And we do it again. And we do it again. And we do it over and over and over. Because what we know is that every arc is different. So we have all of these arcing events. And then we say, let's hit it with 20K. And then you'll see the arcing currents go up. And then we hit it with 30K. And you'll see the arcing values go up. Right? So eventually you get a curve. You have a minimum and you have a maximum. And then what, and I just draw like almost like a linear, but in reality, it may take the form of this and I don't know, something, right? But once you have two parameters, and you might have more, right? So you may say, well, this is for a horizontal bus. I'll write it a little bit better. You may say this is for horizontal. And at 208 volts. And you might say horizontal bus or a vertical bus. Horizontal versus vertical. This is your voltage, right? That is your short available fault current. Trying to think if there's anything else. A gap, maybe, I don't know, say it's 35 millimeter gap. And that's the gap in between these electrodes. So there's parameters. And you may say, well, I'm going to change my voltage to 480, and now you'll have a whole another set of curves. And you may say, I'm going to change my gap from 35 to 25, and then you'll have a whole nother set of a similar curve. But the bottom line is that you have a series of lines, and I can create an equation that takes in the voltage consideration, the gap consideration, the electrode configuration consideration, and your available fault current as a consideration. So we create an equation to calculate arcing current. So this discussion of calculating the minimum and maximum arcing currents based upon the three-phase bolted fault current, we use the equations that are developed in IEEE 1584 to do that. And those are our parameters. We have the gap in between electrodes. We have the voltage, how much pressure is in the system. We have what the available fault current is. And then we have the electrode configuration, whether it's horizontal, looking at you, or vertical, like in a panel board, up and down. So we have all those parameters, and all of that research gave us the equations to calculate the maximum. And when we say minimum, what do we mean by minimum? So this is your maximum, and this bottom curve is your minimum. And where do those numbers come from? Those numbers come from the variations in impedances. Because no two arcs are the same. So for each of these, so for this 10 kA available fault current, my maximum data point and my minimum data point establishes the what do you call that? The zone, right? You have a maximum number and you have a minimum number. And every fault current, available fault current after that, I have a maximum and I have a minimum. And then I have to just be able to establish an equation that will follow the maximum data points that I have and the minimum data points that I have. So you have two basic equations. And I'll tell you that for the 2002 edition of the IEEE 1584, here was the debate. Here's one of the debated items. Let's draw an axis, right? And let's say that for each of these points, I had, I don't know, one here, 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 and then here, 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 and here, 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 and then here, 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 here. Okay, they don't quite line up, but I'm going to do the best I can and move this over this way. There we go. All right, so there we go. All right, so here's what happened. For the 2002 edition, we had the upper line. And let's say that was this line here. And we created that equation. But for the lower number, for the lower arc or line, instead of drawing a line and creating an equation, they went to a percentage of the maximum. And what they had to do was pick up the stragglers. So you may say that, wait a second, for 10 kA, we didn't have any data points down here. At 20 kA, we had this one straggler that was down here. So we penalized ourselves for a lot of data points, making a very low arcing current for the minimum, because we, instead of drawing a line that did this and calculating and creating that equation, we just went with 80% or 85%, whatever that number is. So we knew it was conservatively lower than what it probably could be. So for this 2018 edition, they decided, Dr. Lee, who's doing the testing, decided he's going to do away with this blanket percentage of the maximum. He's going to take those data points based upon the new data plus the old data, because you never throw out old data. And then he drew the curve that hugged the data points, and he came up with an equation for the 2018 edition of this document. So what does that mean? Well, that means that if I was using the 2002 addition, my lower value of arcing current, my minimum value, is going to be less than if I used the 2018 edition if all other parameters are equivalent. Okay, so they added some more parameters to the 2018 edition that the 2002 did. But if you did the vertical bus, etc., and you made the gaps the same, the voltage the same, your minimum arcing current for the 2018 edition would be a higher number than the minimum arcing current for the 2002 edition of 1584. And it's because instead of using a blanket percentage, they went with an equation based upon the data. Okay, and that's significant if you calculate incident energy because, and I'll explain, you're going to see this in a minute, higher arcing currents can produce lower values of incident energy. So keep that in your mind, and we're going to get back to step 3. So step 3 in this whole picture, step 3 is to determine the clearing times. Now I have to take my maximum and minimum arcing currents and analyze them with respect to the clearing time of the protecting overcurrent protective device. So we have to understand that fundamental as well, that the time, the amount of time that I let an arcing current flow will be dependent upon what we call, it's not in 1584, it's not in 70E, it's not in the National Electrical Code, but we call this overcurrent device the protecting overcurrent device. I'll explain to you why that's significant in a second. And then once you know the clearing times, now you calculate incident energy at both values of arcing current, which will have two different clearing times. So 2 values of arcing current with each clearing time, I calculate incident energy. So I'm going to have 2 arcing currents, 2 clearing times, corresponding clearing times, and 2 values of incident energy. The maximum energy that is a result of both of those calculations is what I would label my equipment with. So remember, my 3-phase bolted fault, I'm going to have a max and minimum. An example of max and minimum would be all motors on, all motors off. Now that's simplest. I could have configuration changes, paralleling switchgear, a lot of other things like that. Then I calculate maximum and minimum arcing currents, and then I determine the clearing times at each of those arcing current values, and then I calculate the incident energy at both values of those arcing currents, and then the incident energy that is the highest is what I label the equipment on. Hopefully that makes sense. Now, it's going to get clearer as we move forward. Incident energy is about current and time. Now, your protecting overcurrent device. Remember, the only way that I can control the amount of current, the amount of time that any value of current is permitted to flow is through the proper application of an overcurrent protective device. What are my options? I can have relays, I can have a fuse, and I can have a circuit breaker. Relays will eventually operate a circuit breaker or the switch that's part of a fusible switch scenario. There are shunt trippable switches on the market. It's a no-brainer that I can shunt trip a circuit breaker. And that's a multi-case circuit breaker. I typically would use a relay on much bigger equipment. So your large power circuit breakers or your medium voltage circuit breakers. But a relay does play into this picture. Now, let's think about a time current characteristic curve. the amount of time that I let current flow will be dependent upon the clearing time, or this resume, the time current characteristic curve, TCC, time current characteristic curve, TCC curve. It's not time current curve, it's time current characteristic. Characteristic is a very important part. This is a characteristic of the curve. The fact that it has a little bit of a swing up there and a little bit of swing in there. That's the characteristic. So if I take a look at this 100 amps Class J fuse, I could let 80 amps flow through it continuously. If I put 300 amps, it will clear in about 50 seconds. If I put 500 amps, it'll clear faster at 12 seconds. So higher currents, faster clearing time. I put 1500 amps and it's going to clear in 0.01 seconds. If I put 20,000 amps, it's going to clear less than 0.01 seconds, probably around 0.004 seconds. That's a quarter of a cycle. Remember, this right here is one cycle. That is one cycle. This first right here, that first hump, that's a half cycle. And this clearing time right here is 1/4 of a cycle. That's a current limiting nature of a device. So what does that mean from a waveform perspective? So this is 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles. That's 6 cycles of current, and 1, 2, 3 cycles of an overload on that circuit. This is an example of a short circuit. You can see the difference between the magnitude of current here and the magnitude of current there. Very large difference. And if I would draw this correctly, it should be asymmetrical. So this first half cycle, what you have here is you have what we call a DC decay. Right? So this first asymmetrical, this is going to be determined by what we call the X to R ratio of the circuit, of the system. That is the impedance to the resistance. What are the X's? Transformers, conductors have X impedance, any caps, things like that. And then the resistance is primarily your conductors. But when you first initiate a fault, that first half cycle is a doozy. It's the most you'll see in the power system for any fault conditions. So if I look at a 600 amp, what I'm going to do here is I'm going to compare a 600 amp molded case circuit breaker versus an insulated case circuit breaker versus a power circuit breaker. All 600 amps. They're all the same circuit breaker ampere rating. But their trip curves, their time current characteristic curves will be different. So if I have a short circuit up for this device at around 600 amps, and this is again current times 100, so that's 10,000 amps of fault current, I will trip in 0.01 seconds. So 0.01 seconds, if you look at this, remember that's 1 cycle, 2 cycles, 3 cycles, 4 cycles, 4.5 cycles here. If this is 1 cycle, this is 0.016. This is 0.008. So if I look at 0.01, if this is 0.008, that's about 0.01. That's what you're letting through. If the fault current is less, this is still a 600 amp, same molded case circuit breaker. So what I'm doing here is I'm reducing the fault current on the same breaker. So I'm at a lower fault current. Now I'm at 0.1 seconds. So 0.1 seconds is 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles and a quarter. That's how much current I'm letting through. And think about what that means to incident energy, right? So that's the clearing time for a short time delay for this breaker. It can be adjusted higher or lower in some cases. A current limiting device will let 0.004 seconds on average, somewhere in that ballpark, a half, 1/4 of a cycle. So now, if you think about that trip curve, you have 3 zones. If your fault currents are low, meaning I'm going to let those fault currents flow for a very long time, you have a very high incident energy because it's low fault currents, long duration. If I'm in this mid-range right here, that's your short time delay. I'm calling that a medium energy because now I'm up to, I could have 0.1 seconds, which remember, that's a lot of cycles of current, but it's still less than if the fault currents were in this area here. And the lowest energy that I can get, if this is my protecting overcurrent device, is when those arcing currents are high. So, this is what a lot of people don't understand. Higher fault currents will give me lower values of incident energy because higher fault currents produce higher arcing currents, which put you into the zone of protection for a very fast clearing time. That is a critical piece of the pie. You've got to understand that aspect. Now, this is the 600 amp. Remember I said earlier. Anyway, so here's what we're going to do here. We're going to take a 600 amp, 3 different breakers. A multi-case circuit breaker is the first one. That's the trip curve for a 600 amp multi-case circuit breaker, and I have the same fault current flowing through each of these, which is, if this is times 100, where's my pen? So that's, there's your 10,000, 20,000, 30,000. Make sense? All right, so okay, so you got 10, 20, 30. So 30,000 amps. Just make sure. So this is 30,000 amps, 30 kA. My clearing time is, if we just used 0.01 seconds, I'm at 0.64 calories. Now, I'm going to put in an insulated case circuit breaker. And again, it's still 600 amps. But you'll notice the difference between the curves. I had a short time delay. This short time delay picked up around, if this is 10,000, that's 9, 8, 7, 6,000 amps. So that's 6,000 amps. 5, 4, 3, 2, I don't know, maybe 26, about 1,600 amps, something like that, is where my short time delay picks up. On this one, 10, 20. So this is still 30K, right? And 30, 29, 28. That's 10,000, 10, 20, 30. This is 10,000, 9, 8, 7, 6, 5, 4. This is 3,000. So this picks up just around 3,000 amps. Remember the other one was around 1,600. 3,000 amps through, this is 30, 40, 40, and this is 50, so about 45 kA. From 3,000 to 45 kA, my clearing time is 0.1. This is 0.2. Say this is about 0.16, somewhere in there. So that's the difference, and that's how you read this curve. So you know what your current is, you come to the clearing time, you come over, and that tells you how much time you're going to let any given current flow. So this is 12.7. So the only thing I did, everything else exactly the same. The only difference is that I put an insulated case circuit breaker, and what's the difference between the breakers? Look how big that is in comparison to his hand. Why would I make an insulated case, a breaker that's 600 amps, that is much bigger than that device? Why do I have all the beef? And that's because I need those contacts to stay closed longer at higher fault currents. Look at this delay. That short time delay, the short time delay on this molded case circuit breaker only goes from 2600 or 1600 to 6000 amps. And that's at 0.1 seconds. I can't, if I would apply this same curve, that performance curve, to this breaker, you would have an unintended rapid disassembly in the field. Why? Because these contacts can't take that much current for that much time. So we make a trip curve to protect the circuit breaker. That's what it's there for. I need to clear that fault current where it's possible, and I can't let too much current flow through this device for too long, else I have too many magnetic forces that it cannot hold it together. So in many cases, the trip curve settings are there to protect the device itself. So it can't withstand high fault currents for very long periods of time. This is 30,000 amps for 0.1 seconds. So this is 30,000 amps for 0.1 seconds. Look at what this 30,000 amps, I need to take it off very fast. So the breaker is larger because I have bigger springs, I have bigger contacts, I have more contacts, and all of the springs are bigger. The metal in the arms for the contacts are all bigger and heftier. And then I go to a power circuit breaker. Now these are beasts. I mean, I could put a double wide power circuit breaker, and I could have an interrupting rating. A short time delay, I could have no interrupting rating. The instantaneous value is at the interrupting rating. So if this is 65,000 amps, I can say the instantaneous can be set to 65,000 amps on some of these breakers, depending upon which one you bought. And I can hold those contacts closed for 30 cycles. And that is still a 600 amp breaker, but it's bigger, it's beefier, and it's holding those contacts closed longer so that all those little brothers and sisters downstream can do their job and isolate the faults for selective coordination. You'll typically see these larger breakers up there at the service entrance equipment. So all I did between these three breakers is just add time. And I went from 0.64 to a 600 amp molded case circuit breaker to 12.7 insulated case circuit breaker to 31.8 power circuit breaker.
We'll never trip that breaker.
Now this is a series of videos.
Wow. Yeah, perfect.
So that video showed basically a sequence of events. You had the initiation. Remember, we talked about this. You initiate the fault. It causes the plasma. The current flows through the plasma. What we didn't anticipate was the trough being blown off, not because of the pressures, but because of the cable whip in that trough. All of the light, all of that heat, all of the gases, and it basically fills that room, and you have a lot of pressure, a lot of sound. You have sound, shrapnel, pressure, molten metal being spewed, you have intense light, and hot air, heat. Anywhere where you see the at sign, anywhere where you see that greater than sign, that is because we pegged the meters. So 437 degrees at the hands, over 2,160 pounds per square foot at the chest, more than 437 degrees at the neck. Now the next video basically puts a faster clearing time on this device.
There it goes. We got it.
So all I did was reduce the clearing time. Okay, and what I did there was I kept the fault currents the same, but I moved the curve to the left. I put a smaller fuse in series. Okay, that's like taking a power breaker and putting in a molded case in its place. You've made the overcurrent device act faster. And I got lower temperatures. Temperature of the hands was still up there. Lower pressure, lower dBs, and lower temperature at the chest area. Now the next one is even a faster acting fuse. I gotta zoom in for this one. And that's it. That's it. So there was no data. No change in temperature at the neck, no change in temperature on the chest, no change at pressure on the chest, and no change at temperature on the hands. Why? Because I put a smaller fuse for the exact same circuit, meaning I went in the current limiting region of the overcurrent device. Now I can have that happen by reducing the overcurrent device or increasing the fault current. So all of these parameters impact the arcing current. So these are parameters that are in the equation for arcing current: frequency, voltage, electrode gap, electrode configuration. These are your different types of electrodes. Remember we said we have a vertical bus, and then this is a vertical VB, vertical bus with a barrier. And then we have a horizontal bus. So if you were sitting here facing it, the energy is coming directly at you like a freight train. In this case here, the energy is flowing and you're here. You're watching the freight train pass you, but then it hits the bottom and then bellows out towards you. Then you have your open air vertical bus. That's the energy's going down. And then you have your horizontal bus open air, energy still coming out, but there's no barriers over here. That's what's missing. Those, you're not funneling it out. Now, the protecting overcurrent device, I've mentioned that term a few times so far. What do we mean by that? If I am performing work in this panel board right here, and if there is a main in here, that main is not what determines the amount of energy that will be released if I'm doing justified energized work in this panel. Because I have to assume line side propagation, or if I accidentally touch the line side lugs of this panel board. The actual clearing time is going to come from an upstream breaker that is feeding that panel board. So I'd have to know what my fault current is here, know what my short circuit and my arcing currents are here, determine the clearing time based upon the overcurrent device that's upstream over there. And that will give me my clearing time and my arcing current, and I can calculate my incident energy. And you have your barriers, you know that, arc flash boundaries, that's the distance. Your arc flash boundary, that we want to get to 1.2 calories per centimeter squared. So what we do is we calculate what, at 18 inches? That's your working, that's hands to chest, okay? 18 inches. And then we keep going back until we hit a number of 1.2 calories. 1.2 calories per centimeter squared, and that's where we establish our arc flash boundary. After that point, the energy, the further away you get from the arc, from the event, the lower the energy is. So, and then we had some, I'm just looking through some slides here. We had some changes in the National Electrical Code that sought to reduce the amount of energy that we are exposed to. So what we did with 240-87 and 240-67 was we actually put in some requirements to say, if you're at a circuit breaker that is 1200 amps and above, then you need to have an arc reduction technology, and we gave you options. And there are a lot of different options on the table. Even to meet the requirements in 240-87 or 240-67, you have options. But even beyond that, if you just look at safety by design, there are a lot of different options on the table. There's these types of systems where you have a bucket and a motor control center that you can rack out without removing the door. So you have a handle that comes out and you rotate that and it backs the bucket off of the stabs. And anytime you have an object like that takes a tool, you can add a remote capability to turn that while you're outside of the arc flash boundary. They've added windows. There are people that manufacture windows. So instead of opening a door to do an infrared scan, you can keep the doors closed, right? So you can avoid causing an arc flash event and still get the data you need to determine whether or not you need to pull maintenance. Remote monitoring capabilities. If I want to know what voltage is, instead of sending a person down to the front of a piece of equipment, I can get it remotely. I can also open circuit breakers and possibly close circuit breakers remotely from a phone, from an iPad, from a computer, from a different state, from a different country. Doesn't matter. Just be careful about cybersecurity. Then you have these types of adding distance. These are types of robots. This is a medium voltage breaker that can be racked out from this little robot. There are other types of switches that can be placed on the front of smaller breakers. It doesn't matter. I mean, you can get a remote actuator out there from manufacturers, multiple manufacturers, who make solutions to get you away from the center. So here's an example.
Wow. So the first rotation's really slow.
Okay.
And then after, make sure everything's
It's
okay.
turning very slowly.
And then it's monitoring the torque the whole time. So if anything would happen, it would stop it.
Okay.
It's still turning. That's being pulled off. So, and you'll see what happens
A
here.
couple times anyway, so don't
Yeah.
surprise
No, you're fine. I'm
Yeah, sure. Talking to the camera.
You're being pulled off of those stabs. And then you'll watch the shutter. The shutter will come down. See those shutters come down? That prevents you from that covers the exposed parts. So now you're able to rack that medium voltage breaker out from a distance, and all of that occurs while you are well outside of the arc flash boundary. So this is what they call a chicken switch. That's another solution. You want to avoid being in front of the equipment. I don't care what condition the equipment is in. Anytime you can get an electrical worker outside of that zone, here's what happens. You create a habit. Move people further away. We can reduce incident energy, the arc flash reduction maintenance system, substation primary vacuum circuit breakers. You could have, again, arc reduction technologies. Current limiting devices like fuses are like one of the most efficient devices that we have out there to clear fault currents. Differential relaying. Remember, in the zone of differential relaying, the gazintas have to equal the gazaltas. If there is any difference, if you have more current going in and less current going out, it will trip. And vice versa. The crowbar active arc flash mitigation systems, these quenching technologies, phenomenal what they can get done. Zone selective interlocking. So when you have a zone selective interlocking, if you have a fault outside of the zone of protection, the current going in the upstream is the same current that goes to the downstream. The upstream device goes as programmed. As programmed. And remember, if they don't selectively coordinate as programmed, they will not selectively coordinate because you have zone selective interlocking. ZSI has nothing to do with selective coordination. If I have a fault in between the two, then this guy goes without delay. He goes without an intentional delay because the downstream, no current, no fault detected. So this guy here does not see the fault. This guy does see the fault. This guy knows because they're talking to each other via basically twisted pair that has a voltage signal. When the upstream device sees the fault, it looks at that twisted pair. If it doesn't see a signal from the downstream device, it trips without a delay. And this is the difference. For a fault in between here, you go down to 7 calories per centimeter squared. And if you don't have that, you're at 43.7. All right, so we are well over our time. But hopefully, you got a little flavor for how we calculate energy. It's calories per centimeter squared. It's the amount of heat. I don't calculate force. I don't calculate the amount of sound. I just calculate heat. And we'll label equipment for heat. You have to wear your ear protection. You have to wear your personal protective protection for heat. And when it comes to the force, there's nothing I can do for you. Wear your hard hat, wear everything else, hope for the best. But because if you're in an arc flash event, I don't care how much PPE you have on, it's going to be a traumatic experience. It can change you forever, physically and mentally. Arc flash events are not something to take lightly. It's voltage and current telling you they're there in a bad way. So we talked a little bit about 70 National Electrical Code, talked a little bit about 70E. Don't forget to go out there to NFPA link and get your membership. So you have access to all of the latest and greatest that NFPA has to offer. And I believe that's today's session. So hopefully you got something out of today. Thanks for joining in. Thanks for spending your July 4th with me, 12 o'clock Eastern, here on IAEI News Live. Remember to take care, stay safe, and please stay healthy. See you next week.